welcome. So in this lecture, we're going to do a bit of a warm-up to Riemann sums and integration. So we'll start with something that you should by now know. So recall, and if not, now you will know. So recall, if the cost ct is a function of time t, so if we have that the cost, and I'm going to do this, well, okay, we'll do this like this. So the cost, I'm going to do this in green. So the cost ct is a function of time t. Right? Then we know that the rate of change of this cost c of t, right, with respect to, and remember we write with respect to as WRT, so with respect to time, it's always good to know what you're taking the derivative with respect to is, and then I'm going to do this in orange, this is going to be dc dt, right? And then there's a picture that goes along with this, so now I'm going to have, let's do my axes in red here. So I'm going to have t, and this is going to be y equals c of t, right? And then we're actually going to graph. So if I took this graph, and this was actually y equals c of t is the graph. So a point on this graph, as we recall, this is going to look like t c of t, right? Then we would actually have, so dc dt would give me the slope. At the time t. Okay, so we have this picture in mind. So then the question that we're interested in now as we move into integration is, what if we start with the rate of change of cost? So what if start with, actually I like changing this to green. What if we start with the rate of change of cost? So that's this dc dt. And the question becomes, can we then retrieve the cost increase over a time interval? And the answer is yes. Okay? And this will be integration. So yes, this will be integration. Okay, so let's go ahead and go through kind of a warm-up example, which I think will be helpful as we move into Riemann sums and so on. So let's do our warm-up example. I'm just deciding the color to do it in. Okay, we're going to do this in green. So here's our warm-up example. Okay, so we're going to suppose that we have So we have dc dt is going to equal the constant 3. Okay, so this is a constant, the cost is increasing at a constant rate of $3 per month. Okay, so this is like the cost is increasing at constant rate. And we're going to say that there are units, so this is going to be $3 a month. Okay, and then we're going to have the time interval. Let's do this in red. So we have our time interval. Is going to be 0, 4. Okay, so you can think of that as like 4 months. Okay, so now we have this picture. So we have, I'm just deciding, so I'm going to do my axes like this. So this is time. This is going to be dc dt. But on this time interval, so we're going to go 0 to 4. We're looking at starting at 0. We're going to 4. Okay. And then we have that at 3. So this is our dc dt. This is our graph. So this is constant. Okay, 3. So this is a point on here is going to be t dc dt evaluated at that point t, right? And then, so now what I'm interested in is I'm going to observe, right, that this area equals 12, right, which is the same thing as, so my cost change is going to equal the same thing as if I looked at the rate of change dc dt, just like if I wanted to figure out, right, if I wanted to figure out how far I'd gone, so distance changed, I do how fast I've been going by how long, so I do the rate of change of this times, so that shouldn't seem too weird to you, times, and then I have this time interval 0, 4. So this is like my time. Okay, and that is going to equal the same thing as, so right, just like over here, so this is equal to 3 times this 4, which is equal to that same area, which is 12. Okay? So this is going to kind of give you something to kind of think about. And then, right, in this circumstance, we believe this, just like if you're going at a constant speed for 4 minutes, then how far would have I gone? I just would have multiplied that constant speed times that time that I'd gone. So what if the rate of change isn't constant? And that's the big question. So, oops. So what if the rate of change isn't constant? Right, so here's my big question. So I'm going to box it because this is kind of a lot of what we're doing in this portion of the course, so it's worth boxing it. So what if the rate of change isn't constant? And the answer is Riemann sums or integration. Okay, right. So the idea being, so we're used to taking the function of a quantity or the graph of a function giving the quantity and knowing that its slope is going to equal the rate of change. And now we're going to kind of go in the other direction where we're actually graphing the rate of change, and we want to know how do we get back the quantity, or generally it's going to be like the change of quantity. And the way that we're actually going to do that is we're going to look at the area under that graph, and you can really easily see that starting with a rectangle, because we know that if we're going at a particular rate and it's fixed, so it's like 3 for a period of time, like 4 seconds, then if I want to know how far I went or how much I increased, I would go 3 times 4. And that's the exact thing I would do if I was computing the area, is I would take that rate of change 3 and multiply it by that length of time 4. Okay. But what's going to get a little bit more tricky is that we're going to want to have a changing rate of change. So it's not a constant rate of change. Okay, and in that case, now we have a graph that we have to figure out how to compute that area. And we're going to start out by approximating it with Riemann sums, which you're going to see, again, we're just computing these areas like this. And then we're going to build in by taking limits to actually getting the integral. So I'll see you in the next lecture.